Hello again, friends. In today's lecture, we are going to look at these important expressions. Expression for entropy density, which is total entropy S over volume is equal to this. So let us prove this. Entropy density is rho plus P over temperature. And in the relativistic scenario, we have this. And in the non-relativistic scenario, it is negligible. Let's look at this. First of all, let's prove this expression. S small s means entropy density, and capital S is the total entropy. V is the volume here. So entropy density is given by rho, energy density, plus pressure minus sigma mu I Ni over temperature. According to second law of thermodynamics, we have this statement: total energy, internal energy is equal to T S minus PV plus sigma mu I Ni. This is from the second law of thermodynamics. And we may keep this mu I Ni for now, but later we can ignore it. Okay, so this is second law of thermodynamics, and then we divide by volume. When we divide by volume, and we keep ST term on one side, rest all the terms we have on the other side, and then divide by volume. This is simple algebraic manipulation, and we come to this expression: S is equal to rho plus P minus sigma mu I Ni over temperature. Now you will find this statement in Dodelson's textbook. For almost all particles at almost all times in the universe, the chemical potential is much smaller than the temperature. Therefore, you can approximate this expression as this. Now, next is that for the relativistic scenario, we would like to prove this result. So, what is the value of this small s entropy density for the relativistic particles? For the relativistic particles, the energy is given by this, and pressure is equal to rho over 3. So, S will be, if I put pressure equal to rho over 3, I will have rho plus rho over 3, which is 4 times rho over 3 divided by temperature. And what is 4 times rho over 3 divided by temperature? And rho relativistic is this. So you put the value of relativistic here, and you will see that this becomes equal to this: 4g T cube pi square. And by the this is, so this is of the order of T cube for a given species. As long as the particles are relativistic, its entropy density is the order of T cube. Now for the non-relativistic particles. For the non-relativistic particles, so we have energy density is equal to Nm, and when you put the value of N for the non-relativistic scenario, which we have derived in one of our last videos, you can substitute the value of N here, and we get this. And ignoring again chemical potential, because it remains negligible at all times for all particles, we get this expression. Now, pressure for non-relativistic particles is approximately equal to 0. It is negligible as compared to the energy density. So S is equal to approximately equal to rho over T, where rho is this. So we have mg, g is the degrees of freedom, divided by T, mt by 2 pi 3 over 2 e to the power minus m over t. And then for the non-relativistic energy, this entropy density is of the order of mt 3 by 2 m over t e to the power minus m over t. And by some algebraic manipulations, I can see that it is of the order of t cube plus this additional factor. Now this additional factor, there it is of the order of t cube, and here it is of the order of t cube, and then there is additional factor. Now this additional factor which we have here in the non-relativistic scenario, there are two factors. One is that as the temperature drops, this term increases. So which means this term contributes to increase in entropy as temperature drops. But then there is much higher contribution which is coming from the second term. And what the second term is doing is that it is causing decrease in entropy. So as temperature drops, this term has much more significant effect than this term, and hence the entropy because of this term becomes negligible in case of non-relativistic scenario. So as compared to the relativistic entropy, the non-relativistic contribution is negligible, and that is because of this term e to the power minus m over t. Therefore, when we are tracking entropy contribution, we will only take into account the contribution from the relativistic particles. When we are tracking entropy of the universe, so when we are tracking the total entropy or entropy density of the universe, we will take into account only the contribution which is coming from the relativistic. So non-relativistic contribution is negligible. And that is a very important thing that we must keep in mind. Entropy comes from relativistic particles. Thank you, guys.